Okay, so the nickel or the platinum or the palladium surface invites a hydrogen to come stick to it. And so hydrogen just kind of comes down and sticks. And when it does, it takes its electrons and forms this bond. Okay? When you put the alkene in, the alkene also does that. The alkene comes in and says, oh, I have those pi electrons sitting out there. I'll just go ahead and put those onto the surface. So the active metal invites the electrons between the hydrogen atoms and the pi electron of the alkene onto the surface of the metal. It's kind of a weird mechanism. You don't usually see a mechanism this way. So when this carbon sees that, it says, oh, well, here's a kind of a cool thing. We'll just go ahead and bring our electrons over and we'll form a bond here. And you can see that's what happened. We just formed a new electron bond between the hydrogen and the carbon. Okay? So this is kind of the theory, if you will, as to how this hydrogenation process works. So this is called hydrogenation. Okay? Now, hydrogenation is actually has a kind of an interesting place in our world. Very, very prominent, probably about a decade and a half ago, 2 decades ago, because there was this whole scare. Because here's what was happening. If you take a triglyceride, I'm not going to draw the whole thing, I'm going to draw part of it, because if you take glycerol and you make so these are called 2, 4, 6, 8, 10, 12, 14. They're always even. So that's lauric acid right there. Okay. Lauric acid is a natural compound that, or excuse me, that's linoleic acid, not lauric. This is a natural compound that has a double bond in it. Okay. And there's another one here. So this just duplicates. So I'll just do this, and then it has its kink, and it does that. Okay, I just want to draw them all out. But this is what's happening. These are called, and they're all. They're all cis. Remember cis or Z. Okay. So this is what a triglyceride, something like corn oil or something like canola oil. This is what they actually look like. And what happens with this is the cis bond here causes these big salamis to not stack very well, so they remain liquid. So this is a liquid. So scientists realized, well, wait a minute. We could take alkenes and hydrogenate them to alkanes. So if they take this and they hydrogenate it, and this is the difference between ruthenium and nickel. Industrial uses ruthenium and nickel. Bench chemists use platinum and palladium because they're just more expensive. So it's hard to it's just more expensive to use. So what happens with these, again, liquid? They hydrogenate them in these massive stainless steel vats, and they're supposed to get out the alkanes. Okay. Now the alkane, because it has these big greasy tails, is a solid. So what happened in probably late 60s, early 70s, and through there, the chemists realized that, oh, we could take something like a corn oil or a safflower or a canola, nice natural God-made oil. We can throw it in these big vats. We can hydrogenate it and make this gelatinous solid. And then we can add a little butyric acid in and put a little yellow food coloring in it. We can call it margarine. Okay? But here was the problem. The reactions don't go 100%. Sometimes what you actually get in here is a rearrangement of one of the alkenes to this. What did I just make? I made a trans. So if you remember, there was this massive, and still is today, happened about 2 decades ago, no trans fats. Remember that? Or if you look on a lot of packages right now, a package of chips, it'll say 0. It won't say no. It'll say 0, because there is some still in there. It'll say 0 grams of trans fats. Isn't that interesting? So 0 grams trans fats. And so what was happening was they were realizing that in the process of this hydrogenation, they had some hidden trans fats, and this has been linked to cancer. Okay? So that's the whole reason why some of these reactions, alkenes and alkanes, actually are pretty relevant in our society. Also important to understand the chemistry. Okay, questions on that? And I think the big one that I remember, I think it was it McDonald's? One of them was like the first to switch over to 0 grams trans fats in their fry. And people were complaining because it does have a different flavor, and the French fries didn't taste the same. But now we're pretty much all oils that we use today are 0 grams trans fats. But anyway, kind of interesting. Okay? All right. So the difference again between the nickel and ruthenium, is that going still? The difference between these are typically used, these are used in industry, so that these are industry, mostly nickel. Sometimes they'll use ruthenium, but for these big vats of these things here, it's going to be nickel. Dr. Gallus and I, when we do chemistry in our little bench lab, in synthesis lab, we have palladium and platinum up there that we use. Okay, so those are kind of just where those differ. They're a little more expensive, but they're also more reactive, so better for us. Okay. Any questions? Good. Okay. Now, last reaction that we're going to learn for today, before we kick off, because we're done in here at 5 after, correct? Is that right? Yeah. Okay. So the last reaction that we're going to learn is what I like to call a pair of molecular scissors. Pair of molecular scissors. So if I take, get rid of that. Okay, if I take, okay, so if I take an alkene, oh, by the way, I failed to mention, just put it in your notes, what reaction was that going from an alkene to an alkane? Was that an oxidation or reduction? Reduction. Okay, it added hydrogen, so put that in your notes. That's a reduction process, which is why I brought that up, because we're talking about oxidation reduction. Okay, so there's a really cool reaction that deals with ozone. Right? Ozone can be generated in the lab pretty easily. You can get little ozone generators and you bubble in the reaction. It has a really distinct smell. If you've ever smelled electronics when they're really hot, they have a really distinct odor. That's ozone. It's a real distinct odor. I just think it smells kind of good. It smells like a computer lab to me. But that's what ozone is, and it's basically it is making ozone in the back of the within, especially when they had the old tube. We don't use vacuum tubes that much anymore, but back in those days you smelled it a lot. It was really pretty cool. What ozone does is ozone is a pair of scissors right here. Okay? It cuts that bond. It's really cool. So I could take an alkene and I can cut it right in half. Okay. Isn't that kind of cool? That's what it does. All right? So depending on what type, so if I go from an alkene, I go to an aldehyde, ketone, or carboxylic acid. Okay? It depends on what the functional group on there is. So for example, if I take this molecule, okay? So if I take pent 1-ene, okay? If I take pent 1-ene, and I hit that with ozone, I get out I get out butanal and formaldehyde. Okay, cool. So that's where the molecular scissor comes in. And the best way to do these is just take a different colored pen and just put a line right down through it. Say, there it is. Okay? So I'm going to put an oxygen here, and I'm going to put an oxygen here. So you can see that that oxygen makes an aldehyde. There's a hydrogen here. There's 2 hydrogens implied here. So you can see that the aldehyde is here, and the other aldehyde is here. Okay? If I took something like 1,2-dimethyl cyclohexene. So if I took 1,2-dimethyl cyclohexene and I hit that with ozone, I get out something kind of cool. I get out a double-headed ketone. Isn't that kind of cool? So again, it's a molecular pair of scissors. It just cuts right through the alkane, right? And why do we mention this in this chapter? What's going on with that carbon? What are the carbons undergoing? Oxidation. This is an oxidation reaction. Isn't that kind of cool? It's a very practical reaction, by the way. It's a really fun one to use in synthesis, and we'll add this. So as you build, I will start to use reactions. How do we form alkenes? Okay. How do we form ketones? How do we form aldehydes? So as we begin to build our synthetic toolbox, we're going to show up to a few job sites and actually use our tools. Okay. And we're going to do synthesis, and we'll work synthesis problems typically towards the end of the chapter that we're working on. Okay. Okay, awesome. All right, we'll pick it right up on Friday. So we'll trudge along to trudge.